In the first example, we'll look at the case in which we can ignore the lower order terms when we use the big theta notations. Okay, so the quadratic function here, which is 1/2 or 0.5 times n squared minus 3 times n. This is a quadratic function. And we say that this function belongs to the set big theta of n squared. Okay. So then we would like to, so this is actually something we can infer from the previous lecture. Right? In the previous lecture, we said the worst case and average case running time for insertion sort is a kind of a quadratic function, but we ignore the coefficients in the running time of insertion sort, but only use the big theta notation. So now we would like to formally prove this is actually the case. Okay, we're using the definition of big thetas. So following the definition of big theta in the previous video, we need to determine 3 constants, which is C1, C2, and N0. Okay, we need to determine these positive constants such that the target function here, Fn, is sandwiched by the C1 times n squared and C2 times n squared for all the n's that are sufficiently big. This is strictly following the definition of big theta, right? As long, so let me state this again. As long as we can find the constants C1, C2, and N0 such that the target function is between C1 times n squared and C2 times n squared for n that's greater than N0, then we are done with the proof. And then we can state that f of n belongs to the big theta of n squared. Okay, so the key is to how that we can find, how to find the C1, C2, and N0. Okay, so we just use these 2 inequalities, right? We have 2 inequalities here, right? This one and this one. And we divide by n squared on both sides. It will yield such a new inequalities, right? The n squared is gone and the n is gone and becomes a denominator because we divided by n squared on both sides. So here's the new inequality. And we can further, if we choose any constants, right, that's any constant C2 that's greater than 1/2, right? By the observation, we can show that this left half always hold if C2 is greater than 1/2, right? Because n is always positive. So 3/n, it's always positive. 1/2 minus something positive is always smaller than itself, right? So we can choose the C2 that's greater than 1/2. The right inequality will always hold. Okay, so we kind of solved C2. So let's look at C1. Okay, so now we see that the whole thing in the middle, we can find that the whole target function in the middle, it will increase with n. So when n becomes bigger and bigger, eventually the 3/n approaches 0. So the biggest or the limits of the target function is 1/2. right? But it's always, in theory, it's always smaller than 1/2. But as n increases, the target function always increases, right? So, so we choose the n such that the target function has a positive value. When n is 6, right? When n is 6, the whole thing is 0, right? When n is 5, the whole thing is negative, right? So a negative number cannot be larger than a positive number C1. So we should not consider anything that's smaller than 5. So we should consider the n that's greater than or equal to 7, okay? When n is 7, the target function is 1/2 minus 3/7, which is 1/14, okay? So 1/14 is a positive number. And as long as the constant C1 is smaller than or equal to 1/14, then for any number that's greater than 7, the target function always have the value that's greater than 1/14, right? Because the target function is monotonically increasing. So the left inequality will always hold true. Okay, and we also determined the number of n0, right? Which is 7 here, right? So we determined C1, which is 1/14, and C2, 1/2, yeah? And the target function is always can be described by the big theta of n squared hold, okay? So this is true. We proved that this is true, okay? So to recap a bit, in order to strictly prove that the big theta notation holds, we need to basically determine the quantities C1, C2, and N0. And we need to solve, or we need to find the values of C1, C2, and N0 by solving the inequalities by definition. And of course, there are other choices for C1, C2, and N0. But, right, we said as long as C2 is greater than 1/2, so we can find C2 equals 1, or C2 equals 2, or infinitely, the infinite number of choices. And for C1, it's also infinite number of choices. But the point is that we want to find some choice. We need to prove that some choices exist. That's the most important thing we want to do. It doesn't really matter what these values are, right? But we want to prove that they exist in order to prove the big theta notation, okay? And what those constant values are, they can depend on the coefficients of the target function. Okay? If the target function changes, then the corresponding C1, C2, and then 0 also changes. So that's our first example proving the big theta notation. So in this second example, we are going to show why a higher order function cannot be described by a big theta notation of lower order functions. The example we use is that the cubic function 6 times n cube cannot be described by the big theta of n squared, right? Intuitively, we found that the function in the big theta notation is a lower order function. And intuitively, we kind of know that a cube function cannot be sandwiched by 2 quadratic function, because a cube function always grows faster. It will eventually grows higher than the quadratic function. But now we want to strictly prove it using the definition. So this is how we do it. So we suppose that the quadratic, the asymptotic relationship holds. So suppose that the cube function can actually belongs to the big theta of n squared. So then we must find some C2 and N0 such that the cube function is lower than C2 times n squared for all the n that's greater than n0. That's by the definition, right? So now we've got a inequality. So we can simply divide n squared on each side, and then we've got n should be smaller than C2 times C2 over 6. But notice that because n can be arbitrarily large, so n can be anything, any large number that's greater than n0. So, but C2 is some constants. So this is a contradiction. We cannot have this inequality hold for all the n that's greater than n0. So this is an inequality and contradiction. That's why our assumption is false, which means the cube function doesn't belong to the big theta of n squared. Okay, so this is a formal proof of why higher order function cannot be described by a big theta of lower order functions. The third example we will introduce is to show the big theta notation of a generic quadratic function, okay, in a generic form. So assume that a generic quadratic function looks like this. We have arbitrary coefficient a times n squared plus b times n plus c, right? And we assume that a is greater than 0, okay? Because we want the function to be non-negative. If something is negative here, then the function will be reaches the negative area. All right. So we want to show that this function belongs to big theta of n squared. That means we want to find the C1, C2, and the n0, such that the target function can be sandwiched by the lower bound and the upper bound for all n that's greater than 0. Okay? So it's a bit tricky here because we don't have concrete numbers. We've got a and b and c as constants. So we've got to solve these inequalities in a trickier way, but it's still solvable. Okay, so we can move around the higher order terms, right? We can, for example, move this term C1 into this term and combine these two terms. So we've got a minus C1 times n squared, right? So we've got the inequality on the left, right? It becomes this way. And we can also move the term on the right to combine with the higher order term here, and we've got the inequality on the right to be this form. Okay, so now we have two inequalities to solve, and by observing the inequalities, we find that they are all quadratic functions, right? So remember the shape of a quadratic function is always a bell-like, right? It has a bottom depending on the coefficient of the quadratic term. So a function such as y equals x squared minus x minus 2, the shape is the open is upwards, right? If the quadratic term, the highest order term has a negative coefficient, as shown by the blue upward open. Okay, so if we want some quadratic function to be positive than 0 for all the n's, then we must have the quadratic term to be positive. So if we want this quadratic function to be greater than 0 for all the n that's greater than n0, then we must have this term a minus c1 to be positive, so that the quadratic function is in the upward shape, right? And if we want the quadratic function to be smaller than 0 for all the n that's greater than n0, then it must be facing downwards. The open must be facing downwards. Okay? So we must have this term to be smaller than 0. Okay? So we need to have a between C1 and C2. Right? So, and the n must be greater than, the second condition we want to satisfy is that the number n must be greater than the larger root of the two equations, right? So assume these two equations. So these two, by solving these two equations, we can basically find the 0 points. The root that belongs to the root means that the value of n's that make these functions value to be 0, right? So they can be noted, they can be denoted by these 0 points, like these 4 points here. Okay, so the n must be larger than the roots, because when n is exactly the root values, or it has the same values as the roots, then the function's value is 0. Okay, but we want the functions to be greater than 0 or smaller than 0. So the n must be greater than the larger roots. Okay, so by solving the roots here, right, we can, so first of all, we can choose the C1 and C2 properly, so that it's easier to solve these two equations. Because as long as we choose the C1, C2 by satisfying this inequality, then it's okay, right? We can choose basically any kind of C1, C2s. But we found that if C1 is a over 4 and C2 is 7 times a over 4, these two equations, they are easier to solve. Okay, so after substituting C1 into the equation and C2 into the equation, we can solve this. We can solve the roots of these two equations, and we choose the larger one among them. So by finding, so far we have found the values for C1 and C2 and N0, which satisfies this condition. Okay, so having this effort done, we are going to show that the generic quadratic function can be written by, belongs to the big theta of n squared. Okay. And as an extension to the previous case, if the target function is a generic polynomial functions, so now we're talking about even higher order functions, polynomial terms. For example, the function looks like a0 times a0 plus, so this function can be written like a0 plus a1 times n plus a2 times n squared, right? Until the highest order term, which is a d times n to the power of d, right? So and the highest order term has a positive coefficient. So in this case, it's a very general form of polynomial functions. And in this case, we will have the function belongs to the big theta of the highest order term, the big theta of n to the power of d. So it's totally determined by the highest order term here. So, and for a constant, it's a special form of generic polynomial function. So a constant is a degree 0 polynomial, and it can be basically expressed by the big theta of n to the power of 0, which is big theta of 1. So that's why we have used big theta of 1 before. Okay, so here's the fourth example is a special extension to the, or it's a more general form of the case 3.